Okay, so what I'm going to talk about today is I'm really just going to give you a kind of high-level overview of some of the work that we've been doing in order to sort of give you kind of an insight into some of the concepts involved in, on the one hand, the safety issues for UAS, unmanned aircraft systems, and on the other hand, some of the concepts involved in what the particular approach to safety that we follow, which is safety cases. So if you're interested in UAS, perhaps you'll find some interesting, useful things there. I know at least some of you are working in that area. And if you're not interested in UAS, but you're interested in the safety of other safety critical systems, then hopefully you'll find something there as well. And before I go any further, I'll just say, UAS, unmanned aircraft systems, is the official term. Formerly it was UAVs, unmanned aerial vehicles. The move from vehicle to system was kind of a recognition, it was promoted by the US Air Force, that really system level considerations are very important. But I'm fully aware of the fact that in the newspapers and everything, everybody calls these things drones, and the people who work in this area don't like it very much, but I'm getting used to it, so you can call them drones. I won't publicly get annoyed with you, but so this means drones, right? But I'll probably call them UAS or UAVs. Okay, so I guess all of us, read the newspapers, even people who are not working in this area, so we're kind of aware of the fact that these things are becoming much more prevalent. And, I sometimes try to get my kids, and usually fail, to impress my kids in what I'm working on. But I think of, technology, the two things that are going on right now that are going to make the biggest change in our lives in the next, 10, 20 years is probably self-driving cars. I'm imagining autonomous vehicles is going to be an amazing thing. And then UAVs, UAS. But actually I think this is probably going to be the more amazing thing. I mean, cars, we see cars driving around on the roads, and okay, so maybe now people will be sleeping and the car will be driving, but it's still going to be a bunch of cars on the roads. So, it's a big deal, but this will be a bigger deal. I mean, you look out the window and you will see these things flying around all the time. That is going to be a big change. Not entirely for the better, but it's going to be a big change. So this is, important. And, people have talked about, you've probably read about, all the different kind of mission concepts that people have talked about. Google is getting into this, Amazon, so package delivery, surveillance, making maps and so on. Lots and lots of things people are doing this. But in order to really understand, kind of some of the issues, you have to understand the whole design space of missions that people will do. Oh, and I'll use the word mission a lot. It's sort of a NASA word. Mission really means system. So, we think of doing something with something, we call that a mission. That's the word we use. So, you've got the various mission concepts, then you've got to consider all the different kinds of environments. Are you working in an unpopulated area, in a populated area? Are you in controlled or uncontrolled airspace? And what that means, that's a very important distinction for anything, flying, is are you working in an area where air traffic control is basically providing some services? And ICAO, which is the international body that exists above the various civil aviation authorities in the various countries, has sort of defined, you can go in the Wikipedia and read this, various classes of airspace. And each of those has sort of different rules to follow and, different obligations and so on. But basically, controlled versus uncontrolled airspace. And then there's also low and high density airspace. And, all of that affects how you want to think about it. And then there's the whole sort of range of different, configurations for the vehicle itself. So, we've been talking in the summer school about all the different kind of sensors you can have, all the different kinds of actuators. And then, because it's a system, not just a vehicle, you can think about what your infrastructure on the ground is, what are your ground control stations, do you have ground-based surveillance and so on. So all of those different kind of things need to be thought about. And then there's the operating mode. And here, one important distinction is it visual line of sight or beyond visual line of sight? And what that basically means is, can you see the thing or not see the thing? And that's a very, very important distinction, because basically right now the law is you've got to be able to see it, visual line of sight. But to do anything useful, it's got to go beyond visual line of sight. So everybody is, all the companies are all pushing for beyond visual line of sight. They think they can do it, and the regulators in all the different countries think they can't do it, so there's, a fight going on. And I'm actually, the example I'm going to be talking about is actually about, reasoning about the safety of a beyond visual line of sight application. Okay, so when we talk about the safety, we basically have to make a distinction between design and operational. And basically the idea is that design assurance is saying, I've built some system and the design of my system is such that I think it's going to be safe, and I'm going to provide you the engineering evidence and some judgment and rationale and what have you that show that it meets its purpose, whatever that purpose is. So I clearly articulate what the goals of my system is, and I design it in such a way that it meets those goals. That's design assurance, right? And that's often what people think of when they mean about assurance, or maybe they would call it verification and so on. But you also have to worry about operational assurance. And what that means is, now when I put this thing, when I field this thing, that I keep it safe, and that's also very important. And actually, really, when you sort of reason about a system and when you actually want to get approval to use it, you also have to talk about how you're going to go about operational assurance. And what that means is that you're going to sort of gather data, as it's going on. You're going to do your maintenance, whatever that is, and you're going to reason about how often you do your maintenance. Runtime information might be about software, but it's also about, what's failing, what's not failing, and so on. And when you do your safety analysis as part of your design assurance, you're basically saying that there's certain things I'm going to do are going to keep my system safe or assured or what have you. And in operational assurance, I've got to basically check that actually is the case. So there'll be some assumptions I've made. Do those assumptions actually hold, in fact? Or you've got certain kind of safety barriers that you've designed into the system. Well, are they working? So you've got to check those things. So all that's the operational assurance. So two halves to assurance: design and operational. Another basic principle is that safety measures should be commensurate, is the word they like to use, with the risk posed by intended operations. And again, this is a theme that's come up in several of the talks about, are the measures you're putting in place, cost effective? And this is sometimes phrased as risk-informed safety. So basically, you have to take the risk into account in determining what the safety measures you put in place is. So, our human lives at stake, you're going to spend a lot more money on that. So basically, you've got to figure out the consequences in order to determine what are the safety measures you're going to put in place. Okay, so those are some of the sort of high-level sort of areas that you need to be thinking about. And depending on the sort of regulator and the sort of the regulatory environment that you're working within, there's different techniques in which you can actually do this assurance. But what I'm going to be concentrating on in this talk is one particular technique called the safety case. And this is because I think it's sort of an interesting thing to be doing work on, but also because in the particular area where we were working, this was actually required. And here and there in this talk, I'm going to mention various sort of regulations. You can look these up if you really care about. In this particular case, the FAA, which is the Civil Aviation Authority in the US, they require safety cases for a particular class of UAS operations. So I'll be describing that today, what we did, and tomorrow you'll be making your own mini safety cases. Okay, and another part of that safety case is assessing that you've met an acceptable level of safety. So another thing that people have often talked about in some of the talks here this week is, the impossibility of sort of verifying something as being free of bugs or, being completely safe and so on, and that's absolutely true. So, in safety, we never talk about it's safe, or if we do, we mean that in an informal sense, or it's verified. Instead, all you're ever doing is determining what the residual risk level is. You're saying I've reduced it to a certain level, and I accept that, and that's it. That's all this risk assessment's all about. It's like lowering the risk to a point that you're comfortable with. And what does comfortable mean? Well, various standards or various definitions of that. Interestingly, at NASA, what this means is, how senior is the person who has to sign the document that says it's okay? So if I have a certain level of, for UAS operations, if I'm doing some mission and there's a certain 1 in so many, chance of some accident happening, then maybe it's okay for me to say, let's do it. And if it's higher, my boss has to do it. And if it's 10 times higher, his boss has to do it, and so on, up the chain, up to a certain level, but it's the equivalent of the person who's like running, NASA has to like sign off on it. So that's kind of one sort of intuitive notion of what acceptable is how senior is the person who has to say it's okay. Anyway, that's what risk assessment's all about, acceptable levels of safety. All right, so another kind of fundamental concept in UAS assurance is the notion of airworthiness. And as I said, safety is a concept which really only makes sense at the system level. Now, part of the system is the vehicle itself, and really, when we talk about safety of the vehicle, what we mean is airworthiness. Now, formal methods people like to talk about, correctness, right? Correctness of software, and and sometimes safety of software. And safety people then sort of get a bit annoyed and say, like, like those idiots, don't they know what safety means? It doesn't make any sense. Software can't be safe or unsafe, And that's true. you know, unless you mean this informally in the sense of, you know, what is the contribution of the software to the system level safety? And if that's what you mean, fine, then you can talk about software safety. But really, safety is a system level property. And when you're talking about the vehicle, really what you mean is airworthiness. And airworthiness is really the generalization of correctness to sort of physical systems. And what it really means is that the system, in the case of aircraft, is sort of basically able to do its objectives. It can take off, it can fly, and it can land, you know, correctly, right? So that's sort of a combination of correctness of the software, reliability of the hardware, and so on. So if you want to be talking about, you know, verifying software formally, then really that's part of the airworthiness. Now, I'm sort of making some effort here to talk about airworthiness because that's not what our group has typically been doing. We've been considering the sort of the system level aspects. And if you really, obviously you have to think about both of these things, but I'm just sort of trying to lay out the space here of all the different considerations for safety and how they fit together. So airworthiness is just one of the mechanisms for managing safety risk. And there are other ones that we will get to. So airworthiness basically equals reliability, which includes correctness of software and many other things. But there are other things used in safety risk management. Okay, so what does it mean legally to show that an aircraft or a UAV is airworthy? Well, legally what it means is that the aircraft that you're developing, right? So you bought this, I assume you didn't like build it entirely from scratch, but you bought it from some manufacturer. And that aircraft has a so-called type certificate. And if you're a sort of type theory guy, you can actually, there's an analogy with type theory is not too strained here. So you can think of the aircraft as being a sort of value. And that value has a type, right? You know, so, you know, 2 is of type, you know, int or whatever. And the type certificate basically describes what a well-formed aircraft is. Okay? And so what you have to show, to get an airworthiness certificate, you have to show that you're complying with the type certificate. And you might have made a whole bunch of modifications and so on, and you're maintaining it in some weird way and so on. So there's a bit of effort to go to show that you meet the type certificate. But once you do that, we say that you have demonstrated that your aircraft is airworthy. Now, the manufacturer who makes that aircraft, they had to get another certificate. They basically had to get the type they basically had to show that this type of aircraft is itself, you know, well formed. And so what that means is what they had to then do is they had to go to the regulator and show that it complies with, you know, a higher order kind of design, which is a so-called type certification basis. Right? So basically for any class of aircraft, you have a type certification basis. And what that basically establishes is that certain so-called MOPs, minimum operating performance standards, are met by that design. So, you know, your individual aircraft meets the type certificate, and the type certificate meets the type certification basis. So it's kind of like a hierarchy of models, if you want to make another analogy, showing that this thing complies with this thing, complies with this thing. Now, these MOPs, for UAVs, there's a whole bunch of committees working on these things. They're all under development. I'm probably not up to date on, you know, what the latest is. I know there's committees thinking about these things, but this is something that's like actively being worked on. You know, what are the minimal requirements for UAVs? Okay, now I mentioned that airworthiness is just one of the measures you can employ for, you know, minimizing risk. And basically, roughly speaking, you can think of it as being like a two-dimensional space. On the one hand, you've got your airworthiness. You can try and make your vehicle as reliable as possible, and that's what they do for civil aviation. So aircraft that you fly in are, you know, very, very, you know, airworthy. They're very reliable. But for UAVs, you don't want to do that. You want these things to be kind of cheap. So actually, by design, these things are kind of unreliable. And how do we get away with that? By restricting operations, by really doing very little things with them. So that's kind of like the, you know, the trade-off. You know, you can actually do all sorts of fancy things with your UAVs, but then you've got to be very, very airworthy, very reliable. Or you very carefully limit what you're doing with them, in which case it should be okay to be unreliable. Right? That's basically the combination of the two. And we actually lack very good design tools for choosing the good point in this space. So that's actually kind of an open kind of area. But basically, figuring out what is the optimal balance of these two is one of the challenges in sort of designing, in using UAVs. Okay, so another kind of high-level principle in this area is that of goals-based regulation. Okay, so typically, there's two kinds of regulations you can get. So process-oriented regulation says, do this, and do this, and do this other thing, and then do this other thing, and produce this piece of evidence, and then I will give you a certificate that says you're okay to do whatever you want to do. Goals-based regulation says, articulate a number of goals about what you want to do and justify to me that you are meeting those goals, and then I will let you what you will do. And these are two fundamentally different approaches to sort of regulation. Goals-based regulation is good. I mean, let's say process-based regulation is good in a sort of well-understood area with a lot of history and a lot of kind of, cases of what people have done in the past. Goals-based regulation is good for novel areas. So UAS still counts as a novel area, autonomous systems and so on. So often in the very beginning, kind of goals-based regulation can be very good. Now, what is the means by which you then show that you're meeting these goals? Well, that would be a safety case. So this is one of the reasons why safety cases are often promoted in the area of UAS, is because of this sort of goals-based approach. All right, so what is a safety case? So there's a whole bunch of different definitions of this. I'm not going to give any kind of formal mathematical definitions, but I'm going to give a bunch of quotations. So first one here, this is from NASA Systems Safety Handbook, since I work at NASA. So a safety case is a structured argument with a body of evidence that provides compelling, comprehensible, valid case that the system is safe in a given operating environment. Unpicking that definition, one of the central things is this notion of the structured argument. So a structured argument is basically the rationale for why something is the case. The evidence, well, that's sort of the engineering data that you have, your analyses and so on. And basically what the evidence is doing, what the argument is doing is it's stitching together the evidence and the claims you make about the system. And that's all a safety case is. It's the claims, it's the evidence, and the argument linking the two together. And sometimes I use the word rationale. One time we had a guy from the FAA visited us and we were talking about safety cases, and then we were using the word argument because that is the word, and he got completely the wrong impression that argument is like people punching and fighting and so on. So then I thought, maybe I shouldn't use the word argument. I'll use the word rationale. That sounds like a good word. Okay. Now, what a safety case is one of the criticisms that some people have made of the safety case paradigm is that there are sort of these big analyses you do and then you just sort of throw them away. And there was a very famous case of this, of the Nimrod, which was a fighter aircraft that had a safety case and then it crashed. And people said, aha, that proves that safety cases are useless. And other people said, no, they had a bad safety case, and so on and so on. But really, the way to think about what a safety case is not some sort of analysis that you do once and then you forget about, but rather that it's an active safety risk management artifact. It's something that you use sort of on a regular basis to maintain the safety of your system, and you update it and so on. So that's the way to think about these things. Again, a whole bunch of examples from various regulators here of various flavors of safety cases that have been talked about. Okay, so I'm going to sort of give you a flavor of one particular domain, the UAS domain, and what safety cases look like there. And so here I mentioned that we work with the FAA, which is the US Civil Aviation Authority, and there what they call for in UAS safety cases is that you have a description of all of these things. So you have to describe your airspace very clearly, you have to describe the system, and the system changed. And this is another thing. Typically, when you are fielding some new system, you're not starting in a vacuum. There's always something that exists there already. So almost always what you're talking about is a change in a system. It's very rare that it's something completely brand new. So the more common situation is that you're reasoning about the safety of a change in some system. And therefore what you have to do is you have to talk about what is the existing level of safety of that. So I show that my accident rate is such and such. I have to show that it's not going to get worse. So I have to understand the existing system and then how I'm changing it. So system change is more common than not. Then I mentioned airworthiness, and you got to have a whole bunch of historical stuff. And then remember, this is a system level kind of document. So you're talking about, not just the vehicle, but also the crew and how they interoperate with it and so on. And then there's all sorts of kind of safety analysis type stuff. And I'll be talking more about that later on, as well as the procedures that you use to operate this. So, we've got hardware, we've got software, we've got the environment, the airspace, we've got the people, and we've got the procedures that they follow. So all of these things together is this system. And this is what we need to analyze in order to talk about the safety. And as I said, it's sort of a kind of an active risk management plan. Okay, so another couple of examples of this. So NASA is, not that you're likely to be developing safety cases for NASA, but just for your information. So NASA has actually historically tried to move towards safety cases in the past, and there was some pushback against this. So now NASA is actually promoting a kind of like safety cases light concept that they call objective hierarchies. There's also a thing called risk-informed safety cases, which is basically safety cases, but they just had to come up with their own name for it. Anyway, these are public documents, and so several hundred pages. If you really want to look at it, you can understand some of the recommended methodologies that they're going through there. Okay, and also you might have heard the term assurance cases before, and I probably in this talk will sort of switch back and forth between safety and assurance cases. The idea is that the same kind of, many of the same techniques and principles that you use in reasoning about safety can be applied to other assurance properties, such as security or reliability or maintainability or what have you. And so when people talk about this more general notion of assurance of arbitrary properties, they talk about an assurance case. But by far the most common example of an assurance case is a safety case. So I kind of tend to use safety cases as a proxy for assurance cases. Martin?
Ewan, may I ask, in the beginning you talked about design versus operational
Yes.
assurance.
Mm-hmm.
So how would you, are these two different safety cases? Or is it two different parts of the safety?
Well, in fact, yes, they could be two different safety cases. You're absolutely right, yes. Two different safety cases. The particular standard that I talked about that we used for these UAS safety cases kind of combined them into one document, but there were separate sections. But really, they are separate things. Now, of course, you'll use certain, there's a connection between these. You'll use some things from your design in your operations, and part of your operations is to check that the assumptions you made in your design still hold. But I think you could think of these as separate safety cases. You're right. All right. Okay, so as I mentioned, safety case, explicit articulation of what your safety assurance objectives are, and an argument for showing that the evidence that you bring shows that you can meet those meets those claims. Okay, now another part of it that I'm going to be describing is the risk basis, and I'm going to show you how we provide a risk basis using a so-called safety architecture. Okay. So many different notions of safety case, and the particular one that I'm going to be talking about has this overall structure. So does this work? No. So three components: the argument, the hazard log, and the safety architecture. And those three things together with certain relationships between them, all relying on the underlying evidence. And so I'm going to show you some examples of that for what we have done. And tomorrow you're going to be building one of these things. Now, before I get into sort of the details of this, I would just like to mention another concept. Another concept from in the world of safety, and that is of safety management systems. So perhaps you might have heard of this before. And basically, there's sort of a growing recognition amongst sort of regulators that we kind of need to think at the sort of system of systems level and move towards what they call active safety management. And basically the idea there is that you're not just sort of thinking about individual systems, but you're sort of looking over the whole at the fleet level, and you're sort of analyzing it to find out what are the trends. You're looking for like leading indicators of things that might be going wrong, and you're making sort of principled safety decisions about how you're operating your fleet and so on. So this is the concept of safety management system. It's kind of at a higher level than what I'm talking about, but basically this is sort of the way things are going, and there's various standards, all kind of like very fluffy, if you ask me, talk about what a safety management system is. So I don't think there's any really good principled techniques yet for sort of reasoning about these things, but that is another thing that we need. But that's the way things are going. And just sort of finish off with what sort of things are within a safety management system. Well, here you've got like a high-level sort of safety policies. What are the safety policies that your organization is following? How are you promoting safety within your organization? Safety risk management, I already talked about, and safety assurance of the individual things. Now, all of these things kind of fit together in some kind of vague way that those documents sort of try to communicate. I don't think it's entirely clear, but that's sort of the big picture, safety management systems. But I'm going to be more concrete and talk about sort of safety assurance now, but just to introduce you to that concept. Martin, what time do I go until? 3?
Well, let's see. The panel is supposed to start 3:40.
Okay.
So you have...
Yeah, okay. All right, so safety risk management. Okay, so I'm going to get a bit more concrete now and try and give you some of the concepts that we'll use tomorrow. Okay, so safety risk management. So roughly speaking, here is the sort of high level methodology that we follow. And this is kind of waterfall-y, kind of this, then this, then this. Of course, in reality, it's a bit more complicated and there's feedback and so on. But roughly speaking, this is what you do. You take your sort of data, your description of your concept of operations and so on. Oh, another kind of NASA word, concept of operations, ConOps, that describes the mission. It's also a military word. Your regulatory environment, so what are the regulations you've got to follow, and then what is the change in your system change description, right? So basically this is the input to the thing. And then you do your hazard analysis. You try to identify what are the hazards. And various components of that are, the causes of the hazards, what are the effects of the hazards, and what are the existing sort of safety measures that you have in place, the so-called controls, right? And then you try to sort of assign risk levels to each of those hazards. So that's risk analysis, and then you figure out what are the, the likely, consequences and risk levels of those things. And based on that, then you do your risk control. So, I figure out, what bad things might happen, what is the likelihood and the severity of those bad things happening. Therefore, what additional measures do I need to put in place to reduce the risk to an additional level? So identify a bunch of risk controls. And those are in the form of safety mitigations. Then I need to actually put those safety mitigations into practice, so I have to implement them in some way. And basically then I have to, for each of those mitigations, I have to identify a bunch of safety requirements. Okay, so I go from this all the way down to safety requirements, and then I'll allocate those requirements to some actual system, some hardware, some software, or what have you, and assume the thing gets implemented. So this is sort of the part that I'm talking about here. As I mentioned, you then put this thing into practice, and really what you ought to do is you ought to sort of monitor and make sure that this is actually holding. You actually sort of, monitor and analyze that your safety requirements really are holding up in practice. They're meeting whatever performance measures you've identified for them. And slightly confusingly, the FAA calls this safety assurance. So they use safety assurance for the specific bit of checking operationally that your safety measures actually, are in effect. Whereas most people use safety assurance for all of this stuff. So that's a bit confusing, unfortunately. And that's not the only case of different areas in safety using words in different ways. I'm afraid that's just one of these things. Anyway. Okay, so concretely, so here's the same sort of diagram with some of the boxes expanded. So, we do a hazard analysis, we do a risk analysis and assessment. We have a certain tabular notation for recording these things. We do a risk control and an analysis of that using barrier diagrams that I'm going to be describing. And then we identify our safety requirements and so on. And another part of the story that wasn't really mentioned in the previous diagram is that we want to justify that what we're doing actually, remember this is the whole idea of the safety case, is that we want to justify all of this process. And we're going to do this using structured arguments in the GSN notation, the goal structure notation. And that's going to provide the rationale. So all of this stuff together is what we call the safety case. All right, so now I'll give some overview of some of these bits. And this will just be sort of high level. We'll get into some nitty gritty tomorrow. So hazard log. So this is within the tool that we'll be using tomorrow. It's called Advocate. So what is a hazard log? Well, basically this is going to record. Basically, you'll identify your hazards and you'll record for each of those hazards. What are the environmental conditions and system state in which that hazard happens? What are the causes of those hazards? Precursors. What are the global and local effects of those hazards? And so on. All the bad stuff that can happen. And how might I mitigate the bad stuff? Right. So I'll identify and record all of that within the hazard log. Okay, safety architecture. So safety architecture is actually a phrase that we made up. But it's based on barrier models, which is a well understood idea that we did not make up. And what is a barrier model? Well, barrier models are a particular way of talking about risk. And they're actually I find a very appealing and intuitive way of thinking about risk. Also known as bow tie barrier models, because of this diagram, it looks sort of like a bow tie. And the idea is that for every one of your hazards, so you think, so hazards, and actually this is one of those areas where terms are used slightly differently. So in bow tie world, hazard is used slightly different from in hazard analysis world, I'm sorry to say. But basically, think of the hazards as being all the things that you want to do which are inherently risky, but as a normal part of your operations. So I guess driving a car might be a hazard, or flying your UAV beyond visual line of sight, that would be a hazard. So those are the also sometimes called hazardous activities. Okay, so for every one of those, I want to identify potentially where I might lose control. So these are the bad things, right? This is where I lose control. Where do things start to go wrong? So for every one of my hazardous activities or hazards, I identify my loss of control state. This is also called a top event. And for every one of those, identify all the possible reasons why that might happen. So this is a threat, also known as a cause or an initiating event. So bad things happening, losing control, why does this happen? And then for every one of these, I also identify all the possible consequences. And these are the really, really bad things happening. Okay, now for every one of these, I ask myself, how can I stop, if the threat happens, how can I stop getting to the loss of control? So I put so-called barriers in place. And today, in one of the talks, somebody was talking about barriers. And obviously this is a metaphor based on actual physical barriers, but here we use it in a sort of a more abstract sense of anything you can put in place to stop the progression from left to right. So prevention barriers stop threats leading to loss of control. And once that very bad thing has happened, a recovery barrier stops your loss of control leading to the actual, accident or the adverse consequence. Okay, so that's a sort of barrier model. A bow tie diagram is a sort of semi-formal notation for representing these things. So as I said, top events are the loss of control. You get hazards, threats, and so on. And then prevention barriers and recovery barriers. Now another thing you do in this notation is you say, well, okay, so I've got these barriers that I put in place to stop, bad things leading to even worse things. But what happens if my barriers fail? Well, that's a so-called escalation factor. So essentially this is kind of like a second order kind of analysis. So I have these barriers in place and then, I say, why, what could stop my barrier from being effective, right? So that's called an escalation factor. It's really a threat to the effectiveness of the barrier. You can have it on both sides. And then I can ask myself, okay, suppose this thing happens, how can I prevent that going to here? So then I have my escalation factor barriers. And as a good computer scientist, you probably ask yourself, I can go to the power of n arbitrarily, and in principle you can, but typically it's just sort of two levels here, okay? Now here's an example of that. Okay, so this is from a safety case that we did. I don't know how legible it will be, but here the top event, so here the hazard or the hazardous activity is airborne unmanned aircraft operating beyond visual line of sight. And the top event, the loss of control, is loss of separation. And that basically means that you've sort of gone beyond your safety margin. Your two aircraft are too close to each other. So that's the top event, right? I mean, think of that as being the bad thing. And what are the possible reasons? I can't read it there. So one could be that I have an intruder. Okay, so let's say that some intruder aircraft comes in. What are the prevention barriers that stop, intruder leading to loss of separation? Well, I can have, flight abort, I can have various maneuvers, ground-based surveillance and so on, or, various emergency procedures, okay? Now, emergency procedures involves, a bunch of folk calling each other up on their, radios, okay? That is what people will do. But what happens now, what are the possible escalation factors for this? How can this fail? Well, my radios might fail, right? So or whatever, the communication network might go down. Okay, so that's an escalation factor for that barrier. And if that happens, then what do I do? Well, I could have another radio, so redundant radios and so on. And so on and so on, right? So you can imagine doing this for all of these. So many hazards, many loss of control events, many top events, many threats, many consequences and so on, and all of these can have escalations. And obviously each one of these you can think of as being one risk scenario. Then you've got a gazillion of these things, they all kind of overlap with each other. So what you want to do is you want to get an idea of the big picture, and so that's what we call the safety architecture. And essentially that's a composition of all of these bow ties together in a way that sort of keeps them all consistent with each other.
For a reasonably complicated, complex system, how many top events would you have?
I can't really answer that question all that well, because all we have done is, all I really know about is our own examples. I mean, another point, I'm not ignoring your question, Martin, is that these things are supposed supposed to be abstract and high level. This is not supposed to be a low level, highly detailed, complex analysis that sort of gets into tons of detail. So it should be kind of simple. And you know, part of the reason for that is the main purpose of a safety case is to communicate. It's to convince a human being that your system is safe. That's the purpose of it. It's not to be consumed by a machine. It's to be consumed by, you know, a human. And you need to. And I was actually very surprised when I, you know, first came to understand this. That, you know, what happens is that, you know, like this safety guy told me, like, you better have no more than 10 points. Tell me what your 10 most important, you know, hazards are, and that's it, no more. And I was, what? But, you know, there's more. That's people have limited time, and you know, you don't want to make this too complicated. Anyway, I'm not really answering your question, Martin, but I don't know, like 20 for this system or something, maybe.
I was thinking more
The whole
like,
document is like 150 pages.
okay, I was thinking more like 42.
Could be. It's a good number.
Actually, we had something similar like that for driving automatically on the proving ground, which is much easier than that. We came something about 40, I want to say, 40 lines of actions and
Yeah, I mean, again, you know, it depends on, you know, it's, you know, effort commensurate with risk. So, I mean, I know, I have not myself worked in the manned space program. I mean, I know people who do, and there the level of effort is, you know, 1 or 2 orders of magnitude more than what we're doing here. If you have, like, you know, the safety case for, you know, Orion or something, you know, some spaceship that people are going on, they're going to do far more work. You know, these are basically expendable aircraft, right? So you know, only so much effort they're willing to put on this. You know, so that's just another thing to bear in mind. You know. All right, so we talked about the hazard log. Actually, I'm also including in here the requirements because that's part of that. So I'm not going to say too much about that. There's many different ways in which you can sort of represent requirements. For our purpose, the important thing is really that this is completely illegible, but we'll make some of this in the tool tomorrow, that basically the safety requirements are induced by the hazard. So basically what you want to show is that, you know, understand what are the mitigations for each of the hazards. Each of those mitigations will have multiple safety requirements. You want to talk about how you verify those requirements, and basically what is the tracing between those requirements and the other components of your safety case. So that's sort of what we'll capture in this sort of table here. Okay, and then the third key component of the safety case is the argument structure. Okay, and this is where we provide the rationale for why certain things are the case they are. Okay, so I mentioned that we're using this GSN notation, the goal structuring notation, and the idea here is you can think of it sort of analogous to a proof, in the sense that basically it's a sort of top-down decomposition from sort of high-level to low-level claims. So, you know, the high-level claims are sort of the thing you want to show, and then you recursively decompose those into subclaims and so on until you get down to sort of low-level kind of axioms, as it were. And the axioms are the things that you then provide evidence for. And there's a particular orientation for documenting this kind of reasoning. So these rectangular boxes are for claims about the system, or also known as goals. Additional information about the claims is given in the form of context nodes. The decompositions are done in terms of strategy. So a strategy is basically, you know, like an inference step. You get sub-goals. And then these circles are where you convey, you know, what is the evidence that you're relying on, the so-called solutions. And there's other sort of auxiliary nodes you can use. So you can have assumptions, where you explicitly lay out what your assumptions are, and justifications. Why is a particular strategy, you know, relevant in this particular context? So it's just a way of making explicit what is often implicit in various regulations and in various safety analyses. Just to give you an example of this, so for example, imagine I wanted to show that, you know, system failures for my lithium polymer batteries are reduced to some acceptable level. Well, to talk about this, I can only talk about this in the context of some failure modes and effects analysis of the system. And then I might have two complementary strategies for reasoning about that. I might reason over redundancy. And this box here means that I've not developed this further, so sort of more to be done here. And that relies on an assumption about some independence assumption. So I state explicitly I'm assuming some independence here. And then here I reason over the failure modes. So these are alternative strategies. They're sort of complementary. And the justification here is that the failure modes are actually legitimately characterizing whatever the system. So that's a justification for applying this strategy. And this will get me two sub goals, which would be, for example, that the short circuits are eliminated and that thermal runaway is mitigated. And in order to show that short circuits don't happen, I have some analysis and I provide that here. And then the thermal runaway would require some more reasoning. So it's just a kind of very short, toy example just to show that we bring together the various elements of an analysis. So instead of just sort of throwing in short circuit analysis, I'm showing how this thing relates to that thing. And just as a sort of an aside, I work in a formal methods group with a lot of formal methods people, and often I ask them, well, you're doing some, for example, I have one guy I work with, and he does static analysis, and he does buffer overflows all day long. That's all he ever does is, reasoning about buffer overflows. And I say, well, can you tell me, why is that important? Can you explain to me? And the thing is, if you actually sit down and think about why some formal analysis of one specific thing about a piece of software actually has a bearing on system safety or system goals, it's actually non-trivial. And often you have to go through many sort of layers of reasoning to sort of link those low-level software properties to high-level system properties. It's a bit of effort that has to be done, and often it's not done by the people working on these analysis techniques. Anyway, okay, so this is just another sort of introductory slide. This is actually work that we did with Boeing. I'm not going to get into the details. These safety cases can often be very large and complicated, and one of the challenges here is that because you're not following a specific process, you're more or less free to do whatever you want. It's very hard sometimes for people to sort of understand where to get started and how to go about creating one of these things. So in work with Boeing, we sort of came up with this sort of tiered assurance approach where there's sort of a hierarchy of concerns and you think about these various things, and it just provides some structure to the safety case. Anyway, we have a paper on that. I'm not going to give too many details about that. Now, I'll really have to rush now, 15 minutes, I think. Okay, so now I'm going to give you an example that, again, to give you the flavor of how we did this with a safety case that we created for NASA. And I think Martin has sent you papers. Each of us suggested one particular paper. The paper I suggested describes the safety case that we created for the UTM system. Okay, UTM stands for UAS Traffic Management. And again, some slight contention here about what UTM means and who invented the word. NASA claims they came up with the idea of UTM and it specifically refers to their UTM, but I know some people in Europe are talking about UTMs in a generic sense. So anyway, when I talk about UTM, I mean the NASA UTM. So basically the idea here is that, we got air traffic control for manned aircraft. So what are we going to do for unmanned aircraft? Well, we need something similar, and so that's this concept of the UAS Traffic Management System, the UTM. And so I know there's ones all over the world now. So NASA's been developing this concept, the UTM, and the idea is they're concentrating on sort of low altitude UAS, but that's below 500 feet. And basically, envisaging sort of these UTMs being deployed all over the place and basically sort of scanning, the airspace and maintaining safety and sort of taking requests to fly in a particular area and so on, and all sorts of cool functionality. But basically, multiple concurrent fixed rotary wing, small UAS, that's another thing. This is only for small drones, and supporting both visual line of sight and beyond visual line of sight. So it's quite kind of a rich sort of concept, UTM. And so NASA is developing this concept, this UTM concept, and the way it works in the US actually is that typically large government research labs develop some concept and then they pass it over to industry, and industry implements the thing. So that's how it's working with the UTM. So NASA has sort of developed this proof of concept, and now some companies are competing to actually build and sell these things. So what we were involved in was actually in developing a safety case for NASA to test their prototype proof of concept. And in particular, part of the concept is beyond visual line of sight. So they wanted to reason about the safety of flying beyond visual line of sight. And as I mentioned, that's one of the current major impediments to promotion of UAS in industry. And so we had to sort of reason about the safety of that. And the paper that you've got in your package is actually talking about how we reason about that. And you see here some sort of eye candy talking about some of the various elements of that. So we analyze the airspace, we analyze the risks, we identify requirements and so on, and we basically sort of stitch all of these things together in the form of sort of rationale. Okay, I'm going to skip over some of the details. A high-level overview of what our concept of operations is like, multiple UAVs of various kinds, flying in a particular configuration, beyond visual line of sight. What are the key safety concerns? In other words, what are the top events that they worried the most about? Loss of safe separation, that's sort of two aircraft coming too close to each other, and flyaway, exiting the designated range that they were allowed to fly within. So those are the two things they worried the most about. And loss of safe separation could mean either two UAVs sort of coming too close to each other. It could be, crashing into the ground. They use the word loss of safe separation as a very, abstract way of talking about crashing. Loss of safe separation from the ground, and also between an unmanned aircraft and any kind of intruder aircraft. This test was carried out in an agricultural area of California. So there's a lot of aircraft for like dusting crops and all that kind of stuff. So they were worried about colliding with those. And then a bunch of other things. GPS, so I think it was yesterday, somebody mentioned that GPS is unreliable, and indeed that's the case. And in fact, when we initially submitted their safety case to the FAA, one of the feedback we got from them was that we hadn't sufficiently taken account of the fact that GPS is very unreliable. And so we had to add some additional procedures. And one of the things that we had to worry about was space weather. So space weather is basically, cosmic rays and what have you, and solar flares and so on, and they can like interfere with your GPS. And so we had to have procedures in place for actually mitigating that. And there's actually sort of websites where you can actually track space weather and so on. So we had to make that part of our procedure. Okay. So anyway, remember we talk about safety in terms of sort of changes to systems, and so we have to figure out what is the first. Of our worst case consequences, we have to figure out what is the unmitigated risk. And what that means is, before I put any safety procedures into place, what is the likelihood and the severity of the really bad consequences happening? And so it was determined that the likelihood of a mid-air collision was actually probable. And the definition of that, what does probable mean? It means happening once in every certain time. So the very interesting talk on autonomous vehicles actually sort of got into some of these numbers. And so probable actually really means that it's, the odds are that it will happen between once a week and once every 3 months. So it was determined that that's probably how often we're going to crash. So that's pretty bad actually. And how likely are we going to crash into the ground? Again, there was a certain, identification of a certain kind of risk levels. Okay, so then, given that, now we want to reduce that to a lower level. So those are unacceptable numbers. What we do is we want to identify various safety strategies. And here I cite two particular safety standards. So MIL standard 882 is actually very popular and has actually influenced many other standards, many other safety standards, including this NASA standard actually. They're all publicly available. And typically what you do is, when you're looking to sort of reduce risk, there's a hierarchy of safety strategies that you follow. So some things are better than others. And so this is from better to worse. So eliminate the hazard if you can. Just get rid of it. Just don't have it happen. That's the best thing. And if you can't do that, control it in some way, sort of lower it. And if you can't do that, have some device in place that sort of works around it in some way. And if you can't do that, warn people about it. And if you can't even warn people about it, then just train them to sort of operate with it, properly. And if you can't even do that, well, tough, just accept it. That's all you can do. And if that's not good enough, just get rid of the system. So that's kind of the hierarchy of safety strategies. We talked about that in our working group this afternoon.
So when this satellite was shot down, that was re-entering, is that kind of...
Which satellite is that?
There was something, I think it was during the Bush administration, the second Bush administration.
Okay.
There was something that was shot down, and...
By the Chinese or something? I don't remember.
No, I think because out of service.
Okay.
Maybe it could have been another. Would that be an example of the last case?
Well, no, not really. I mean, that means basically just like give up and don't use your system. Just get rid of it. That's what I'm saying.
Okay.
And sometimes that's the right decision. And
where would something like that fit into the...
Well, imagine you got a nuclear power plant, say, and that's a, you know, a highly potentially unsafe kind of thing, and there's lots and lots of, you know, safety analysis going in there, and actually safety cases are used in that area. And, you know, sometimes the right decision could be just to like retire the thing, and that's it. It's reached the end of its life. And part of the, you know, the art of safety management systems is having sort of principled decision-making processes for doing that. You know, when is it the right thing to do that? And so that whole kind of decision-making process is, you know, what goes into safety management. Right, I'll try and sort of press on. Okay, so in the safety case, there's a bunch of safety measures to be identified. The paper talks about these a bit more. Okay, so how do we do risk assessment? So this is actually an abstraction of one of those bow tie diagrams here. Again, you can't see it. It's a pity they look so rubbish when the images are you know, at this level. But basically, the idea is that we want to compute what is the likelihood of these events happening, these consequence events happening. So I know what my initial risk level is for these, and I want to figure out what's my residual risk level when I put all my barriers in place. And roughly speaking, what you do is identify the likelihood of your threats happening and identify the so-called integrity of the barriers. And integrity is basically, you know, what is the effectiveness of the barrier in preventing this proceeding to here. So you come up with numbers for that. How do you come up with those numbers? Don't ask me, that's very hard. And everybody argues about that, and there's no good answer. But try and come up with numbers for this and for this. Given all of those numbers, you can apply a not very sophisticated probabilistic formula to get a number here. And that's what we did. So basically we had all of these bow tie diagrams I talked about. We composed them together to make the safety architecture. We abstracted into this sort of form. We come up with numbers for, you know, the likelihoods of the threats. You know, how likely is it that some, you know, intruder is going to fly in here? And why do you think that? We come up with numbers for the integrities for each of our barriers, and then we get our residual risk levels. And then you can look at that and you can say, well, is that acceptable? You know, do I think that's low enough? If not, you need more barriers. And so it's a sort of a way of helping you to design your mission. Okay, now, barriers basically is the same as mitigations, right? So it's another word for the same thing. You then have to implement those. That's where requirements come in. So for every one of those barriers, you can identify a bunch of safety requirements. And in our case, for this mission, we were using radar, so we had requirements on the radar. We had to choose where we're flying the UAV, so we had to sort of design. This is a sort of map of Central California. We had to sort of design, you know, the location where we're going to fly. So that's part of mission design. Some sort of analysis of the geometry of the airspace. So we had to sort of figure out what that is, and this actually has a bearing on procedures, because what this diagram is telling you is what to do when an aircraft flies in a particular location. So you've got to design all of those procedures. And procedures are, you know, affected by human beings, so you've got a bunch of different individuals who are communicating in a particular way, so each of these is a different role, and so they all communicate with each other. And this is actually separation limits, which is telling you how close you're allowed to fly to in various different criteria. And then lastly, for UAVs, we had various avoidance maneuvers that were designed. So in our case, we had 4: return to base, divert and loiter, blah, 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 terminate, and so on. All of those things together, the requirements, the requirements, you know, the risk analysis and so on, are all stitched together in the safety case. And then, so basically, you know, coming up with the arguments for justifying why all of this stuff fits together, that's sort of the challenge. And then convincing the regulator that you've done all of that. Okay, so that convincing, as I said, is done in the form of arguments, structured arguments, using this goal structuring notation. I'll just sort of race on. Give you a couple of examples of that. So this is that sort of high level, you know, architecture that I described. It's one possible, I don't want to oversell this too much, but it's one possible way of sort of structuring an argument in a particular domain. Different domains will have completely different kind of architectures. And so the bit that I'm talking about here is the functional safety of some of the barriers that we had in place. So, these are completely illegible. So here, what you see is an example of reasoning about why one of the barriers that we put in place, in this case it's the ground-based surveillance system, can actually do its job. You know, why is the radar actually able to detect and track intruders? So I consider all the different components of the system. So the ground-based surveillance system consists of various components. It consists of ADS-B, which is a particular kind of, you know, transmitter communication technology, a range safety display, the radar itself, and so on, reasoning about the geometry of the system. I got to talk about, you know, why the ADS-B is actually going to be effective, you know, in terms of the equipment that's on the vehicles. Why is the range safety display going to work? You know, how am I going to use it? How am I going to calibrate it? What checks and procedures am I going to follow? Pre-flight checks and so on. So there's a whole bunch of things to actually say to explain. If I was speaking, you know, informally to a human and trying to explain to him how I'm using the ground-based surveillance system, I'd probably be talking about many of these things. And here we sort of lay this all out explicitly. And this is just for one of the barriers. Now, another point I want to emphasize about safety cases and sort of argumentation in general is that you shouldn't have arguments everywhere. You only really need arguments for certain things. There's certain places where there's a gap, a semantic gap, and it's not obvious why this thing implies this other thing. Why is that holding? Those are the places where you should use an argument to convince something. Within the sort of the research community of this, people sort of spray these things all over the place where they're often not needed. You know, for well understood areas where there's a quantitative analysis, you know, engineers know what's going on. You don't need one of these arguments. It's just use them sparingly and where it makes sense. And that's what we did in this safety case. All right, then another one we had there. All right, so the last thing that I was going to talk about, but I'm actually going to skip it, but you'll have it in the slides, is, so I'm almost done, Martin, because it's time for the panel, is specific operations risk assessment. And that's a new standard that's being promoted and is actually becoming very popular, I know, in Europe, also in the US. And it's a particular way of getting approval to do UAS operations. And it's basically based on this bow tie barrier methodology that I talked about earlier. So it's something that's sort of going to be useful. If you're actually going to be involved in any kind of UAS missions, you're going to need to know about this SORA. And we had some input into that, so I'll not say any more.
So this is more about operational risks, or does it relate to the
Yes.
integrity levels?
It does, all of that, yes. And they have their own terminology, and it's all very confusing, and they're using words differently from how I use them, unfortunately. But yeah, it's a sort of bow tie barrier based, and it's meant to be very simple, so they have abstracted away many things, and they have a particular kind of, you'll have the slides, so they have a particular kind of workflow where you do a certain kind of analysis and so on, and they say if your risk class is this, then you better do this. So it's kind of a simplified, abstracted process for getting approval for, anyway, I know I'm working with a guy in Denmark, and I know he is working with a UTM service provider, and they have to follow SORA. So if it's in Denmark, I guess it's here as well. I don't know. Oh yeah, I'll end there.
So one follow-up question. In doing complex systems and safety engineering, maybe this is something for the panel, but still, clearly you need knowledge in the domain.
Yeah.
And you also need knowledge in safety engineering. Right?
Yes.
And what's your view and experience in, let's say, composing teams?
That's a great question. I mean, and basically the way that my personal experience is that I'm not an expert in the area of UAS. I mean, I've absorbed some knowledge and so on, but you know, we were only able to develop this by, you know, very closely working with the domain experts. And in our case, it was like two key people we had to work with, and we had many meetings with them. And basically, it's sort of like this sort of, you know, like Socratic dialogue of back and forth, a kind of dialectic, where we would ask them to justify stuff to us. And they would have to think about it. And we would say, well, like, you know, suppose this then what? And they would say, well, you know, here's the reason for that. And I would sort of like write it down and try and formulate it in terms of some kind of reasoning and so on. And then back then, and very often, they would say, well, you know, that's right, I never thought about that situation, and so on, and back and forth, and back and forth. And then we would write it up and we would give it to them to review, and they would say, well, this is right, and this is wrong, and so on. So it was very close coordination with, in our case, it was a pilot, and in the other case, it was a mission manager, so a person who's sort of designing the mission and so on. But ultimately, we were able to influence quite a lot of the design of the mission by talking with them. But you know, absolutely, you have to have both of those roles, the domain expert and the safety expert, for sure.
Okay, any further question? You have your spacecraft on the roof, I believe. Yeah, sure.
Yeah. So when you do the bow tie diagram, so you have one top level hazard, you design your barriers, you start with an added hazard, and and then you figure out, okay, there is something common, we have some common barriers, we have some common causes. And
Oh yeah.
so what do you do in that case?
Oh well, that's a good question. So yeah, if you've got common barriers, that kind of messes a lot of things up. So try not to do that. Yeah.
So probably Herman will maybe touch upon that in the architecture design tomorrow. But yes?
One question. Before, for example, hazard identification, you have something like system description. If you wanted to make hazard identification on the system of system, which is not existing,
Yeah.
I have to identify first object, non-physical and physical, and I will thinking about the wireless and everything what will be connected to the autonomous object. This may be a vehicle or robot or something else. Before I will make hazard identification, I have to go by the steps. Is any limits of abstraction in this?
I mean, are you basically talking about where do I draw the system boundary in that case? If like it sort of goes on forever?
Yeah.
Yeah, I mean, I don't really have a good answer to that. I mean, yeah, I mean,
Or is some standards or some hierarchy classification of the object that later
Yeah.
I will find the relation and find the events and hazard and so on?
I'm not really aware of it. I mean, I know a few years ago, I mean, also at NASA, people were really pushing system of systems and talking about it a lot. And so I read on this and tried to understand it a bit more, and then it kind of all went away, but don't talk about it much.
For example, I mean, you were mentioning the traffic management.
Yeah,
Clearly it has to manage the system on system. So,
yeah.
so it seems like,
I just call it system.
yeah,
But you're right.
It must be more complicated system.
Yeah.
Did you also thought about some connection with the IT security from the hazard identification?
Security?
Yeah.
Again, it's a good question, and you know, again, I think one of the talks mentioned this. Safety and security, very close connections, two separate communities, and many people are working on kind of reconciling these things. In fact, bow tie diagrams have been used for security analysis as well. Your adversities and so on, and your attack surfaces. It's kind of a natural notation for that. There's a few papers on that. So.
that is a very timely question, and because we have a little bit of a CPS security surprise tonight. So, just hang on. Okay, thank you very much, Ewan.